The next step is to introduce a controller for the water feed stream. I open the model palette, F4 in the keyboard, click on Dynamic Control, select and double click on the PID controller. A new controller is introduced. Here it is. I'm going to name this controller water flow controller. The process variable will be the water feed stream, the mass flow as the selected variable. Here it is, the mass flow. And the output, the actuator, will be the valve water feed, the corresponding valve. Actuator desired position, select. Now I have the proper connections. You can check it in the process flow diagram. I need to specify the tuning parameters. I'm going to use the same values than before for the previous controller for propylene oxide. This is 0.1 for the proportional constant and 5 minutes for the interval time. The action is again reverse, because when the flow is too high above the set point, the control valve should be closed the opposite direction. This is a reverse action. The minimum value will be 0 and the maximum double the desired value, the set point, which is 5,000, so double 10,000. The desired set point will be 5,000 kilograms per hour, and the action of the controller automatic. I activate the faceplate and close the controller. I'm going to place it here. And finally, I need a fourth controller, which must control the temperature in the reactor. I open the palette again, Dynamic and Control Group, double click on the PID controller. The name of this controller will be reactor temperature, reactor temperature controller. The process variable will be in the reactor the temperature. I filter by this variable. Many temperatures are available. The one I am interested in is the temperature vessel temperature. And in order to control this temperature, I am using the coolant stream. In this case, a control valve is proposed for selection. This valve is not visible in the system because it is supposed to be inside of the coolant stream. To access this valve, you need to use this button in the lower part of the form. Here it is, where you define how you are going to control this stream. The simplest way is to define direct Q. This means that when the controller selects 0% opening of the valve, this minimum refrigeration will be used, and when the 100 output is selected, this maximum cooling will be used. If we check the actual value of coolant, in the steady state is 1,300 kilowatts. We are going to assume that the maximum available refrigeration is double this quantity. This is 2,600 kilowatts. I go to the control valve. But as this is a negative value, this must be the minimum because it is negative. So the maximum cooling corresponds to 0% opening, and the minimum cooling, which is 0, no cooling at all, corresponds to 100% opening. This is important to determine the action of the controller. You must take into account this reverse selection of minimum and maximum values. When the temperature in your vessel goes above the set point, goes above 60 degrees, the cooling must be higher, must be opened, but this means going to a lower value because it is minimum. So this action is reverse. A higher temperature in the reactor means a response of the controller going to a lower value, reverse action. The parameters I'm going to use is 1.75 for the proportional and 5 minutes for the integral. The set point will be 60. Then I am going to use a range between, let's say, for example, 20 and 100. The action will be automatic, and the set point is not 85, it is 60 degrees. I activate the faceplate and close the controller. For the coolant, just an acceleration comment, direct Q is the most immediate way of controlling the cooling stream. If you want to use a more realistic control, you can select the option from utility fluid. In this case, you are controlling a real cooling stream between a minimum and a maximum flow, but you must specify all the required parameters: the heat transfer coefficient, the amount of coolant inside of the system, the heat capacity, and so on. For this example, we will use the simple direct Q control. I place the reactor. Let me check the integrator conditions. I have a non-stop condition and a 0.05 action. Well, the problem is that in the previous simulations I have run, the temperature of the controller has moved to a very, very low value, -94. When I run the simulation, no dynamic assistant, the system of course goes to maximum output. This means that the coolant is set to 0, but since temperature is so low, 10 degrees, the reaction does not take place, no exothermic enthalpy is released, and temperature cannot go to a higher value. How can we solve this? For example, we can stop. I'm going to use a trick. I will open the reactor. I am going to empty the reactor by selecting a 0% liquid level. Okay, at this point the reactor will be empty as soon as I start running the simulation. Okay, and now it starts be filled with fresh raw materials, and so the temperature can go to a higher value. Now you see, as the temperature goes to a very high value, the output of the coolant is 0. That means maximum cooling 2600. But finally, it seems that after some time the system is finally controlled. Okay, in the next video we are going to describe how to define a strip charts to follow the evolution of these variables. Okay, this is taking long. Let me check just the tuning of the system, the control valve, because I have noticed. Okay, yes, the minimum available, I have the specified kilojoules. It's not correct. The correct value was 2600 kilowatts, which is a much higher amount. Okay, now the system is working, but now the cooling available service is high enough to reach the final temperature. Sorry for this mistake. We only needed to correct the maximum cooling available in the refrigeration unit.